Hello guys, welcome to the Go Code Snippets channel. So in today's video we'll be looking at testing and benchmarking our Go apps. But before we move into the video, I would like to mention that if you are new to the channel, make sure you subscribe to the channel. And if you've been watching videos on this channel for some reason you haven't subscribed, I would actually appreciate it if you subscribe, because that is the way that will help me push my videos out there, and I really appreciate that. So with that, let's get into the video. So for this video I have a package recursion. So this package recursion has two functions basically, a factorial function and a Fibonacci function. So the factorial function, just like the name says, calculates the factorial of a particular number. So let's say I pass in 5 into, it's going to give me the factorial of 5, which is 120, and this here does it recursively. Then this second one here, fast factorial, is just also a factorial function that calculates the factorial of a particular number, but it does it with a for loop, which is more performance than the recursive one, which is up here, because generally recursive operations are usually expensive. They are expensive operations and they kind of slow down performance at when it gets to a particular point. So it's usually advisable that when running a recursive operation, if there is a way to work around it, that it won't affect the code readability that much, then it is always good to take the alternative route. And also the second function is the Fibonacci function, which calculates the Fibonacci of a number. So let's say that I pass in Fibonacci of 1, that was 1, then Fibonacci, or let's say the nth Fibonacci. So this one actually calculates the nth Fibonacci number. So if I pass in 1, this gives me the first Fibonacci number, which is 1, 2, second Fibonacci number, which is still 1, then 3, third Fibonacci number, which is 2, then 4, fourth Fibonacci number, which is 3, then 5, fifth Fibonacci number, which is 5. So that is how this one works. So, and it also does it recursively. Then the second one here is fast Fibonacci. So this one also does Fibonacci, but instead of recursively, it does it with a for loop, which is also more performance than the recursive Fibonacci function here. And when we get to benchmarking, we'll see if that is true or not. So that's it. So let us quickly just go to our main function and see if it works. So I was actually testing it before recording this video, and I have it here. So if I do my factorial first, factorial of 5, so the factorial of 5 should be 120. So when we run the app, we should be having 120. So I'll just go run main.go, and then we have it 120. So if I change it to fast factorial, it's also going to give me the same thing, just for us to see that it is actually working in both ways. Fast factorial 5. So I still get 120. Then for our Fibonacci also, so Fibonacci 5, that's the fifth Fibonacci number, which should be 5 also. So I have 5, and if I do fast Fibonacci 5, so it also gives me 5. So now let us test our functions and see if they are working. So to test a particular function is to test a particular package, or to test functions in a particular package. What you just need to do is, now I have recursion.go as the name of the file, so I want to create another file. So I'll create a new file under the same directory, then I'm going to call it recursion, then I'm going to use underscore test. So whenever I use underscore test.go to name a file, the Go compiler automatically knows that the file is a test file. That is the first thing when you are testing Go files. When you want to test a Go file, always add it with underscore test.go, so that way the compiler will pick it that is a test file. So from there we'll move on. So the first is going to be package recursion, which is the name of the package you want to test. That is the first thing. Then from there we'll do a function. So to write test functions, the functions must always start with the test keyword. Then we can give it any name that we want to test. For here we want to test our factorial function first, so I'll call it function test factorial. This is going to take in a signature, and the signature is actually a signature variable, which is actually a variable t. It can be any variable, but the type is always of type testing dot t. That is type t for package testing, so I have to import package testing. So luckily enough, Go comes with inbuilt unit testing in form of the package testing. Sorry, I imported forms. So this is how it works. So even here already my plugins are already telling me to run test, debug test, because automatically VS Code already picks it. My Go extension that I installed for VS Code already picks it that I'm trying to run some kind of test. So from there we'll have to test the code. So to test it, I'm going to declare two variables. The first one is going to be a got variable, which is basically what I'm getting from my factorial function. So I'm going to get factorial of 5. So what I want as a factorial of 5 is 120. So I'll say if got is not equals to want, that means if our test fails, if what we were expecting, which is what we want, is not equals to what we got, and what we got is actually the return value from the factorial function, we just call t.errorf. Then we can say test failed. Then I can do got %v. Then I want %v. Then I pass in my got and my want. So this is basically it. So from here now, to run this test, I'll just right click on this and I'll open this in integrated terminal. Okay, let me just navigate to it from this current terminal. So for me, I just run the command go test. So go test here, test for all the functions inside the particular package that we are working with. So if I run go test, because the test passed, I'm getting this. So let me fill the test on purpose. I'll just change the ones to 30, for example, or 130. Then if I run go test, then it should fail this time around, just like we're expecting it to. So it's failed this time around because I'm actually expecting it to fail. And this is my fail message from this particular line here. Then test failed. So what I'm getting is 120, but I want 130. So I'm filling it on purpose just to show that the test actually passed. So we'll just write one more test for our Fibonacci also. So I'll just simply copy this here, and I'll test Fibonacci instead of factorial. Fibonacci. Then here I want the Fibonacci of 5, which is basically 5. So I'll change this one to Fibonacci of 5, which is 5. So I will run this good test. So good test run the test for this first function and it passes, and also the test for this second function and it also passes. So when you run ordinary good test, to run the test for all the functions inside that particular package. So let's say I fail this one, for example, and I make the value 10, and I run good test, it will fail because good test runs all the functions in the particular package, so it will fail this time around. So let's say that we have a lot of functions and we don't want to run all the functions that particular package, and we have a lot of functions in the package. We just want to run for a particular function. How do we go about that? So the simple way is just to specify a -run flag. Then it will be equal to, then we'll give it the name of the particular function we want to test as the argument. So this time around I want to test factorial because Fibonacci obviously is failing because I failed it on purpose. The fifth Fibonacci number is 5, not 10, but I don't want to have anything to do with that. I only want to test for the factorial, so I'll just specify it inside the -run flag. So I'm running on a Windows operating system. If you're running on a Mac, I don't think this quotes matter, but if you're running on Windows, you have to put the quotes. So I run this, so it is passing because I'm only running for the test factorial function. I'm not running for this. So if I run for only test Fibonacci, to fail because the fifth Fibonacci number is 5, not 10. So this time around it fails. So this also works for fast factorial and fast Fibonacci. So let us just change this. I'll change this to fast factorial and fast Fibonacci. And one more thing you need to notice is that this particular name here does not necessarily have to correlate with the name of the function you want to test, but always make sure that whatever the function you are using, whatever the test function is, must always start with the keyword test. So that is the take on testing. So if I run this, it will still fail because the fifth Fibonacci number is 5, not 10. so it failed. If I change it back to 5, it should pass this time around. So if you want to actually specify the -run flag, but you want to use it for all the functions in a particular test file, you just put dots. So go test, ordinary go test and go test -run equals to dots are the same thing. So this here runs the test for all the functions in the particular test file. So that is how it works. So the next thing we want to talk about now is table testing. For table testing, we know what we are doing here is we are just actually specifying just one input and we are getting one output. So for that, for table testing, we'll create a type test cases. So let me say type test case, and it's going to be a struct. So going to hold two values, my got and my want. What I got and what I want, and they are all going to be ints. They will both be ints. So in my test factorial, I'll just tweak the code a little bit. So I'll create a slice of test cases. So I'll say test cases should be a slice of test case. Test case. And I want to specify all my test cases here. So the first test case I want to specify here is a factorial of, so my got is factorial of 1, and what I want or what I expect as a factorial of 1 should be 1. So I'll just copy this, copy it like 4 more times. Then factorial of 2 should be 2. Then factorial of 3, that will be 3 times 2, 6. Then factorial of 4, that will be 4 times 6, 24. Then factorial of 5, that will be 5 times 24, which is 120. So I'll just simply say, so I'll cut this code here. So I'll say for index, comma, test case, let me say test case should be equals to range test cases. Let me just make this TC. So I'll do T, this T here, dot run. So use this dot run to run a table test. So this dot run takes into argument. The first one is actually a string that just gives some information on the particular case we are running. So I'll just make this a string formatted text. So I'll do testing for case percentage v, then the value will be the index plus 1. Then the second argument is actually still a function with this particular signature here. So that will be a function that will take in t of pointer to testing dot t. So I'll just simply paste that code here. So I'll change this to got should be equals to tc.got, then want should be tc.want. So I'll first format. So what I'm basically doing here is I created a test case struct that takes in two fields, the got and the want, and they are both integers. Then I created a series of test cases here. Then I'm bringing over the test case. Then for each of the test case, I'm just giving some information to the particular case we are running on. And t.run takes in two arguments. The first one is a string, which is just an information. It can be anything, just to like show the information in the particular case you are running. And the second one is also a function that has the signature of the original test function, which is this. And I'm assigning the gots to the test case got value, which basically are the values here. Then the ones are the test case ones values. Then if the got is not equals to ones, we will give our error information, and we'll also display the particular information here concerning the case that failed or something. So let us just run this. I want to specify as test factorial. I don't want to test factorial So let's run this and we'll see if we have any problem. So everything passed. So let's say I fail one of them. Let me just fill the third test case and give it the value of 10, and we'll run it. So it failed. So here it's giving me the information that testing for case 3, then test failed, got 6, wants 10. So I failed it on purpose. So let me just pass it back, then we will run it. So that is it. So we can also do the same thing for our Fibonacci also. So I can just copy this and I'll come to my Fibonacci and I'll paste it here. So I'll just change the values to Fibonacci. So the Fibonacci of the first number, or first Fibonacci is 1, second Fibonacci is also 2, third Fibonacci is 1 plus 1, 2, then first Fibonacci is 2 plus 1, that is 3, then the fifth Fibonacci is 3 plus 2, which is 5, then every other thing does not change. Yeah, I guess this is just it's here. Then we'll run this for test Fibonacci instead of test factorial. Then the test passed. So if I fail one of them, let's say I failed the 5th case and I give it a value of 12. So here I'm having a failed case. That's for case 5. It's failed. So I'll just return it back. So that's how you do table tests in Go. So pretty straightforward. Just define a set of test cases for this. Then from there, you just range over each test case. Then you call the run function. And the first argument is just some information on the particular case that is running. And the second argument is also a function that takes in the signature. That is like a function that is of the same signature with the original test function, which is this. And always remember that the test function must always start with the name test, and also this name, any name that you want to give this, it doesn't really matter, but always make sure that it starts with test. And also the test file must always end with _test.go. So that is just the take for testing. Then we move to benchmarking. So for benchmarking, I'll just simply comment out all this code. So I'll comment out all this code. Then we'll move into benchmarking. So for benchmarking also, it works the same way with testing. So I have to create a benchmarking function. And for a benchmarking function, the name must always start with benchmark. Even my autocomplete showed me already. So benchmark, and this XSS can be any function name. So I'll call this benchmark factorial. So it's going to take in a variable b as an argument of type testing.p. So if you remember, for our testing, it takes in a variable t of type testing.t. But for benchmarking, it takes in a variable p of type testing.p. So I have to import testing. That is the next thing. Now our benchmarking also works in our one that's called test.go file. So that is how you create a benchmarking function. So that is the first thing. So the next thing is that now we want to benchmark our factorial function. So to benchmark our factorial function, we'll just simply write a for loop. So the for loop will run from for I. So it will run from 0 to b.n. I should be less than, then I plus plus. So what we just simply do is just simply call our factorial function. So let's call factorial of 10. That is basically the benchmark. So to run the benchmark, we'll run go test, then I'll do dash run. I'll just simply put a dot, meaning I just want to run anything that has to do with test. I want to run it, but then I want to also benchmark. So I'll do dash bench equals to, then I'll specify the particular benchmark function I want to benchmark. So I'm benchmarking my factorial function, which is in the function benchmark factorial. So that is it. So use the dash bench flag to specify the particular function you want to benchmark. Now press enter. So So when I run the command, it gives me information about my CPU, then it tells me. So this 4 is basically the value of n, because I'm running b.n times. So this n, yeah, the value is 4. So it means that the whole thing ran 4 times. Let me format it so it looks a little bit more readable. So it's telling me that it ran 4 times. Then for each time it ran, it actually ran 18,913,722 operations or loops or operations. Then for each operation it ran in 57.79 nanoseconds per operation. That's how fast this is. So what is basically benchmarking? I forgot to mention that before moving into the benchmark. So what benchmarking basically is, if I come back to my main.go file and I try to calculate the factorial of, let's say, 40 for example. So I'll just go back, I'll go up a folder and I'll run the main.go file. So I tried to find factorial of 40. So it took a lot of time, but okay, let me run the factorial of, or let me say Fibonacci. Fibonacci takes more time to run than factorial. I also want to show us something. So if I run the Fibonacci, the 40th Fibonacci number, I want to get that, then I run this. This is going to take a whole lot of time. So I have this as the Fibonacci as the 40th number. To my surprise, it's even run fast. So let me try Fibonacci of 50th, the 50th Fibonacci. So this is taking way more time than it should be taking. This is taking a whole lot of time. This is a lot of time. It hasn't still computed the Fibonacci of 50. And the reason is because the Fibonacci function, if you remember from our package recursion, this form Fibonacci is recursive. That is why it's really slow. So what I'll do is I'll simply stop. I'll stop the code from running. So I'll change it to fast Fibonacci instead. Then look at what happens now. Fast Fibonacci. Boom, it runs in less than 2 seconds if I'm not wrong. So let me just quickly just check. So I'll say start. Should be time dot now. So let us just see how long it took the operation to run. So I'll print down here, or let me do print f. Took %v seconds. So I'll do time dot since start, then I want it in seconds. Yeah, that's basically. So we'll run it and we'll see how long it takes. So it didn't even take up to a second to run the whole operation. That is our fast Fibonacci. But if you remember, our Fibonacci was taking a lot of time and we have to wait for this. I even doubt this will even run in a minute. It will take even more than a minute to run. So what benchmarking basically is like a way of kind of writing a function in another way such that it's going to be more performant, like writing a function to perform the same logic. Yeah, that is what, to perform the same logic. Two functions to perform the same logic, but then we are comparing the two functions to see which one is more performance or which one actually goes about the logic faster to improve the performance of our apps in general. That's what benchmarking does. So let's assume that you are working on a code base, maybe we are introduced to a new period and all, and you follow that a particular function is using the way that is slowing down the whole app. So you can actually write on that function that you feel is going to run way faster. Then you can benchmark the two to see if the function you wrote truly works or performs faster and better than the function that was in the particular code at first. So that's what benchmarking basically is. So we are still waiting for this. It doesn't still run. This is really slow. So I'll just cut it. I'll just exit it. I'll break it. So back in our recursion under test_test.go. So now that we've run the benchmark for this, so we can also run a benchmark. So if I try to do a factorial of 50, this is going to take way longer. And I have to command recursion. Then I'll do go test. So this one is telling me that it actually ran still 4 times, so n is still 4. Then this time around it ran how many operations? It ran 3,110,000 operations, and it took 359.4 nanoseconds per operation. If I increase this number to maybe 60, what you notice is that this number becomes smaller, and then the time it takes become larger. That means it is getting less and less performance, because if it ran 3 million operations in 355.9 nanoseconds per operation, and then I increase it, is going to like run lesser operation with more time. So it is kind of getting very slow over time. As this input increases, it gets slower. So now it's running just 24 million operations or 2 million operations compared to our 3 million operations before, and it is taking more time to run each operation, so which is getting really slow. But if I check my fast factorial, for example, my fast factorial does the other thing. So my fast factorial here runs way faster. So this one ran, my fast factorial ran 20 million operations, and it took about just 59.41 nanoseconds per operation. So if we were to compare the two, it has a whole lot of times faster. So this one, my normal factorial function, actually ran 2 billion operations in the same amount of loop n, which is 4 times. Then this one ran 20 million operations. That means my fast factorial is about 10 times faster than my normal factorial method. And if you remember, my normal factorial method is recursive, but my fast factorial method, so if you recall from down here, if you recall from my recursion.go, my normal factorial function is recursive, but my fast factorial function is using a for loop. That's why I said earlier in the video that recursion is a very expensive operation most times, so it's always good to like avoid it as much as you can. And if you can't avoid, because there are some cases that it is actually like the, how will I say, it's like the only way to go. Not really because it's the only way to go, but then it makes the code easier to read and it makes the code look more straightforward. But there are some places that you can actually maneuver and think of another way of writing the same function that won't be recursive, so it will use less resources and then it will be more performant. So that is basically it. So now the next thing we want to look at now is how to also run a table benchmark, just like how we ran a table test. So for that, it's just pretty straightforward. So what we'll just simply do is we'll do our inputs. Let's say inputs should be a slice of integers, and I have 10, 20, 30, 40. Let me just leave it at 40. So I'll just simply say, I'll cut this. So I'll say for underscore for index, comma input should be equals to range inputs. So I'll do b dot run just like I did c dot run. Then the first argument also is still a string that gives us some information about what is going on. So I'll say forms.printf benchmarking factorial for index or for case percentage v, and I'll do index plus 1. Then the second argument is actually a function that takes in the signature for our initial benchmarking function. So if I just do this here, it gives me that. Then I'll just simply paste what I had before. I'll paste it here. Then this time around, instead of having 60, I'll be having inputs in this place. So that is it. So I'll just format the code. Then I'll run the benchmark. So this time I want to first check for factorial first. Let's check for factorial first. Then we'll now check for fast factorial. Then we'll compare the two. So it is running the benchmark. So this is for the first case when the input is 10, then when the input is 20, when the input is 30, when the input is 40. So if you look at it over time, it is getting slower and slower. So this is when the input is 10. So it ran 13 million operations and 104.4 nanoseconds per operation. Then this one ran about 5 million operations. Then this one also 5 million operations. then this one 3 billion operations. So if I'm to like add, let me just add one more value to it, 50. Now we run this again. So this time around, for some reason, it ran faster than the first time. So this time around, we're having 20 million operations for when the input is 10, unlike here that we have 30 million operations. So the results are not actually consistent, but what I really want us to notice is I'll just simply change my factorial here to fast factorial, then we'll compare the two and we'll see which one runs faster. So I'll now rerun the benchmark, then we'll compare the two, then we'll see which one runs faster. So here, when the case was 10 for our normal factorial, we had about 20 billion operations, but here we have 81 million operations. That's about 4 times faster. Then even the time also says it. Here we have about 50.48 nanoseconds, then here 12.87 nanoseconds, which also 4 times faster. Then when the inputs became 20, we were looking for the factorial of 20 factorial, we were able to run 9 billion operations with our normal factorial function. But with our fast factorial function, we were able to run 49 million operations. That's also about 4 times faster, or even 5 times faster if I'm not wrong. Yeah, 5 times faster. So that is it. So basically, if you're to be building an app, or if you're working on a particular project and you're calculating the factorial of numbers, it's always advisable that you most likely know that from this benchmark you should use the fast factorial function for your factorial arithmetic instead of the normal factorial function that uses recursion. So that's it basically. So what I'll simply do here is I'll copy this function. I'll also benchmark our Fibonacci, so we can see our Fibonacci benchmark also. So I'll change this to benchmark Fibonacci. And I'll change this to Fibonacci of the input. So I'll just change, let me just make it 40, 10 to 40. And I'll clear this out. Then I'll run the benchmark for our Fibonacci this time around. This is really funny. On the 40th Fibonacci number, we were able to only run, even though the loop ran 4 times, we were able to just run only just one operation, and it took how many nanoseconds? 1, 2, 3. That's about 1 billion nanoseconds to just calculate only just one operation. That's a whole lot of time. And if we change it to fast Fibonacci, let's see how far or how performance that is compared to our normal Fibonacci function. Let's take this up. Oh, this is really jaw-dropping. A whole lot of times more performance. So this one ran about 2 million operations at 474.7 nanoseconds per operation. And this one ran how many million? 132 million. That is really performant. Far performance. 2 million to 132 million. That's over 200%, over 100% performance. If I'm not wrong, if my math is not wrong, that's over 100. Am I saying this is 132 million, and this one ran in 8.589 nanoseconds per operation, just for the case where we're having the Fibonacci of 10, which is the 10th Fibonacci number. Then for 20th Fibonacci number, this one also ran 50 million operations. This one was just able to run 18,000 operations. So this is far performant and faster than the usual Fibonacci function. So if you're also working on an app and you are computing the Fibonacci or you are for some reason using Fibonacci sequence, you most likely don't want to do Fibonacci by recursion, or it's going to really slow down your app. Imagine this is just Fibonacci, 40th Fibonacci, and I was able to only run one. So if I'm to like add like a 50, let me see, I even hope this will even be able to run the benchmark if I have to add like a 50 to it. I hope the benchmark for the 50th Fibonacci number will even be able to run. But let's see. Okay, this is fast Fibonacci. I want to do for ordinary Fibonacci, not fast Fibonacci. Let's check this out. I doubt if it's going to be able to run the 50th Fibonacci number, but let us just. So that is for the 10th Fibonacci, 20th Fibonacci, 30th Fibonacci, 40th Fibonacci. This is taking it a whole lot of time. Yikes. That means Fibonacci by recursion is not even a good idea, no matter what. It's not even a good idea. It hasn't even still run. I knew this was going to be a problem when the 40th Fibonacci number was able to run only just one operation on 4 iterations. I knew calculating the 50th Fibonacci number is going to give Go a headache. But let's just cancel this, so we won't waste time on it. So I'm playing out the console. So that's basically it for testing and benchmarking our Go apps. So you can also like check the standard libraries package testing for more information and also more build and also more flags to run and benchmark our Go apps. So with that, I'll be coming to the end of this video. But before I end the video, I also like to give my usual ones that if you are new to the channel, please make sure you subscribe. And if you're not new to the channel but you've been watching videos on this channel for some reason and you haven't subscribed, make sure you subscribe. And also if you like the video, hit the thumbs up, don't forget. And also comment, drop a comment below whatever it is that you have that you want to say, maybe a comment or an observation or a criticism, a constructive criticism and multiple criticisms. Just drop everything down in the comment section below. So with that, I'm ending the video. Peace.